So we've spent a week learning how to solve systems of linear equations with two variables and two equations. It turns out that we can also solve systems of linear equations that have three equations and three variables, and this represents three-dimensional space. So we now have an x-axis, a y-axis, and a z-axis, meaning we have an ordered triple for our solution. So we remind ourselves again of the idea of the solution of a system of linear equations. The value of the variables that make all the equations true. Okay, so it turns out that now we have three equations, three variables. So whereas in the past our solution was an ordered pair, now we're going to have x, y, and z. So an ordered triple. Taking a look at our procedure. These can be solved using substitution. They also can be solved using elimination, what our textbook calls linear combinations. And since that's the format that most of my students seem to understand the best and have the most ease of use with, we're going to look at elimination, linear combinations, as a way to solve our three variable systems. The process for that is we're going to work with things that we already know how to do. Systems of two equations, two variables. We're going to use the ideas behind elimination to take two equations at a time and eliminate the same variable both times. So we get two new equations, two variables. We can solve those, plug them back into our original equation, any one of the three, and get that third variable. So the idea of a solution, remember, means that our x, y, and z solve all three of our equations. It's going to be more important than ever that we check our work. Many steps to these solutions means more opportunities to make careless errors. So we want to make sure that we're checking our answer at the end. How does that look? So if we're asked to tell whether an ordered triple is a solution of a system of linear equations, we're going to take our x, y, and z values, plug them in for x, y, and z in each of the equations, and make sure that it solves that equation. So what's that going to look like? Negative 6 plus 2 times 1 minus 2 times 2. We're checking to see if that's equal to negative 8. Negative 6 plus 2 minus 4. Order of operations says all the addition and subtraction in order from left to right. So negative 4 minus 4, well, that's negative 8. And so our first equation checks out. Let's do the next one. 1. So negative 2 times negative 6 plus 3 times 1 plus 2. We're checking to see if that's equal to 17. So positive 12 plus 3 plus 2. 12 and 3 is 15, plus 2 is 17. That one checks out. Let's take a look now at our third equation. The opposite of negative 6 plus 5 times 1 minus 3 times 2. We're going to check to see if that's equal to 11. So the opposite of negative 6 is positive 6. Plus 5 minus 6 equals 11. This one's not looking good. 11 minus 6, clearly not equal to 11. So 5 is not equal to 11. So negative 6, 1, and 2 is not a solution to the system. So now that we've understood how to check our answers, let's walk through the process of solving a system of three linear equations in three variables. To start off with, it's very easy to confuse these, and it's very difficult to describe which equation you're talking about to someone else if they can't see the equation. So I'm going to go ahead and label these equations, equation 1, equation 2, and equation 3. We're going to refer to them that way as we work our way through this example. Before I begin, I'm thinking that I need to combine a pair of equations at a time and do that twice to eliminate the same variable twice. So I want to set up some strategy. I want to think about, do I want to try to eliminate x, or eliminate y, or eliminate z? Well, I'm drawn to z right away because I have two equations that both have one z. It should be relatively easy to eliminate that. And with 4z, I could be able to eliminate a z again with a second pair of equations with a multiplier. Same thing with x, because I have 1x, 2x, and 3x. I could multiply the first equation by -2 once, -3 another time, and be done. It looks like it's going to be a lot harder to eliminate y. Let's take the path of least resistance and try to eliminate the z variable. So I'm going to take equation 1 and equation 3 and add them together. Only difference is I want to go ahead and reverse the signs on equation 1. So the opposite of x plus 3y minus z equals 2. Let's add that to equation 3. 3x minus 2y plus z equals 5. 3x minus x is 2x. 3y minus 2y, 1y. Negative z and positive z equals 0. 2 and 5 equals 7. So I now have a new equation, 2x plus y equals 7, in two variables, x and y. I'm going to label that equation number 4. Now I need to repeat that process, taking another pair of equations from my original system. And we like working with equation 1, so let's take equation 1, multiply it by -4, and add it to equation 2. Negative 4x plus 12y minus 4z equals 8. -2 times -4 is going to give me 8. My equation number 2, 2x minus 5y plus 4z equals 9. Let's add them up. -2x. 12y minus 5y is 7y. -4z and positive 4z, that's going to equal 0. 8 plus 9 is 17. I now have my second equation in two variables. I'm going to label that equation 5. So this is the process. Selecting a pair of equations, intending to eliminate one variable. Taking then another pair of equations, intending to eliminate the same variable, creating two new equations, which I'm going to label equation 4 and equation 5. Two equations, two variables, in this case x and y. Now I'm going to add equation 4 and equation 5, my two new equations, together. 2x plus y equals 7. -2x plus 7y equals 17. Let's solve this by elimination. We did this all last week, and I think as students you guys are doing a pretty good job with this. 7y plus 1y, 8y. 2x minus 2x, that's going to sum to 0. We don't need to write it. 7 plus 17, 24. Now we can solve for y. And we find that y equals 3. Remember, my solution is going to be an ordered triple. I'm going to go ahead and I'm going to open up a set of parentheses, x, y, and z. I know my y value is 3. Let's place that into the parentheses right now. Now that I know y, I can substitute back into one of my equations and determine the value for x. 2x plus y equals 7. So I say 2x plus 3 equals 7. 2x will equal 4. And x equals 2. Let's place x equals 2 into my ordered triple. One step remaining now. We've got values for x and y. We need a value for z. Well, now I'm down to having one unknown. I can solve for one unknown. Use my first equation, x minus 3y plus z equals -2. I know that x is 2. I'm going to substitute it in. I found that y is 3. Let's substitute that in. Plus z equals -2. So I have 2 minus 9 plus z equals negative 2. 2 minus 9 is negative 7. And let's add 7 to both sides. And I find that z is equal to 5. So my ordered triple that's the solution to this system of linear equations is the ordered triple x equals 2, y equals 3, z equals 5.